All right, so let's recap. The length of the whole ramp is 1.22 meters. And again, this is for exercise 2, the calculations. The height of the ramp is 16.2 centimeters. Now, notice how I don't have them the same units, so I am just going to change this to meters just to make sure that I have everything in the right units. I also know that the mass that was required to hold it up was the mass hanger plus 20 grams. It ended up being 68.8 grams altogether. I just massed it. So this was the mass on the end of the string that was required to hold it up, and then of course that's 0.0688 kilograms. Now these are the numbers that we know. We're going to find a theoretical acceleration and an experimental acceleration. So theoretical, you should have remembered this from your pre-lab, mg sine of theta. So m meaning the mass of the cart. Oh, one more thing is this is the mass of the hanger. The mass of the cart is 518.8 grams, or 0.5188 kilograms. But the force acting on the cart on an angled ramp, we have to put the mass of the cart in for m, g is 9.8, and then sine of the angle. Now sine is opposite over hypotenuse, right? So we do have opposite, that's the height, and hypotenuse is 1.22, that's the length. So we're going to put the mass of the cart in for m, that's 0.5188 kilograms. G was that 9.8 meters per second squared. Then we have sine of theta, which is opposite, 0.162 meters over adjacent, 1.22 meters. Okay, that will give us our theoretical acceleration. So grab your calculator and calculate away. I'm going to start out with this, it's easier. So 0.162 divided by 1.22. Okay, then I multiply it by 9.8. Then I multiply that by 0.5188. All right, so I got 0.675. And what are the units? Well, it's a kilogram. These cancel out. Kilogram times meter per second squared. It's F equals MA. It's a unit of force. So it's a Newton. So it's 0.675 newtons. Now, that's the theoretical. The experimental force is what we measured using the hanging mass. And that's just m, the mass that's hanging, times g. So the mass that was hanging was 0.0688 kilograms. Multiply that by 9.8 meters per second squared. And we get the force acting on the cart, the string force. And that should be equal and opposite to the component parallel to the track. So we put 0.0688 times 9.8. And again, why is it 0.0688? So there's a period there. It's 68.8 grams. 1, 2, 3. Move the decimal point over by 3. So I get 0.674 newtons for my experimental force. Wow, that came out pretty darn close. It's actually a lot closer than it was the first one. So now again, what you do is you find the percent difference. Again, it's still a percent difference because even though this is theoretical, quotation marks, this mass was measured. When you measure things and you're comparing it to other measured things, you use percent difference. So remember, that's the difference in values divided by their average. So the difference, you can actually see it's only 0.001, and divide by the average, we actually can do this pretty quick because the average is just halfway between 0.674 and 675. So the percent difference, that's the difference between the two values, 0.675 minus 0.674 divided by their average. And I already know what their average is because what's the average of 0.675 and 674? It's 0.6745, right? I did it not in my head, because halfway between these two, 0.674 is a little bit smaller than this. The halfway point is 0.6745, right? Times 100%. So that would be 0.001. We're going to have a very low percent error on this one, divided by 0.6745, and we get, and multiply it by 100, you get 0.15%, which is really low. I don't know, I must have just gotten lucky on this one. Usually it's not that low. Okay, so that's it for exercise number 2.